Problem 17. A standard dice has 7 as the sum of the dots on the opposite faces. The dice is put on the first square as shown and then rolls towards the right. When the dice gets to the last square, what is the total number of the dots on 3 faces marked with a question mark? So we have a dice whose opposite sums are always 7. So if we have 1 here, the opposite one would be 6. If we have 3 here, the opposite would be 4. Let's pick one side and see where it ends when it reaches to end. So we take first, we come here, it would be the face, the wall. Then the next time it would be bottom, the point 1, and then it rolls again, it would be here, and then it will be on the top, and then it comes on here. So we have this one. 2 will always remain the same, so we remains 2. Now opposite to 3 is 4. So when it rolls, it would be 4 in here. So we had 4 plus 2 plus 1 gives us 7. So our answer is option B, 7. Problem 18. 6 people each order 1 scoop of ice cream. They order 3 scoops of vanilla, 2 scoops of chocolate, and 1 scoop of lemon. They top the ice cream with 3 cherries, 2 wafers, and 1 chocolate chip. They use 1 topping on each scoop such that no 2 ice creams are alike. Which of the following combinations is not possible? And these are our options. So we have 3 vanilla ice cream, 2 chocolate, 1 lemon. We have toppings, 3 cherries, 2 waffles, and a chocolate chip. Each ice cream must have a unique combination of flavors plus toppings. So let's assign the toppings to them. So we have these ice creams. We have 1 cherry, 1 wafer, and then chocolate. So we are done with 2 here, 1 and 0. Then comes 1 cherry and 1 waffle. So we have 1 here and 0. Now what we left is 1 cherry. So we have all toppings unique, and that is what our requirement is. So let's go on the options now. Chocolate with a cherry, yes, we have that. Vanilla with cherry, yes, we have that. Lemon with a wafer, no, we don't have that combination. So that could be our answer. Chocolate with a wafer, yes, this is there, yes. Vanilla with a chocolate chip, yes. So our answer is option C. This is not possible. Lemon with a wafer. Problem 19. The teacher writes the numbers from 1 to 8 on the board. The teacher then covers the numbers with triangles, squares, and circle. If you add the 4 numbers covered by the triangles, the sum is 10. If you add the 3 numbers covered by the square, the sum is 20. Which number is covered by the circle? These are our options. So we have triangles and square. We have only 1 circle. So what does it mean is that when we have all the sum, we can know the sum of the triangles, and we have the sum of the squares. So if we subtract that, we would get a sum of the circle. And since we have 1, so there would not be any sum, but it's just 1 number. And that is what we are looking for. So let's go. So sum of from 1 to 8 would be 36. And sum of the numbers of the triangles we know 10. So we have triangles done. Sum of squares we know it's 20. So 10 plus 20, 30. So 36 minus 30 gives us 6. And 6 is our answer. That is option D. Problem 20. Jan has some pictures of parrots. She wants to color only the head, tail, and wings of each parrot either red, blue, or green, so that all 3 colors are used on each picture. She colors one parrot head red, its wings green, and its tail blue. How many more parrots can she color so that all the parrots are colored differently? Jane has already colored a parrot. And then we have to find out how many more parrots she can color. So we will do it with two methods. One method is about the permutations. And if your school has not taught permutations, then you can follow the method 2. So we have three combinations. So we have three permutations can be formed, which could be make 3 into 2 into 1 gives us 6. Jane has already done one color, so we minus 1 and we gave 5 and we got answer D. Second method, we would use different combinations. So we have already been used red, head red, wings green and tail blue. So she has already done this one. Now another combination. If we take head red, then we can interchange wings and tail. If we take head as green, then we can change wings blue and red. We keep head green, then we can interchange wings and tails to red and blue. We have another combinations, head as blue, we make it red, green, interchange head, wings and tails, make it green and red, and head blue. So how many combinations we have? We have 6 in here combinations. She has already done one, so we make it 6 minus 1, 5 gives us answer option D. Problem 21. There is a row of books of different size on a shelf. There are 20 books to the left of the largest book and 22 books to the right of the smallest book. The largest book and the smallest book are both adjacent to the oldest one. What is the smallest possible number of books on the shelf? And this is a very important word here. Smallest possible number. These are our options. So let's consider. We have 22 books to the right of the smallest book. So we take the bigger one, bigger size book. So we say 22 books to the right of the smallest book. So we have 22 books here, and this positions 23rd, the smallest book, and this is the small. Now we have 20 books to the left of the largest book. So 20 books, and we need to determine smallest possible numbers. So we try to overlap. So we have somewhere here which position as 21st book, and to its left we have 20 books to the large. So this is the largest one. Now this largest book and the smallest book are both adjacent to the oldest one. So we have oldest book in between. This is the oldest one and we marked as 22. Now we have the position for 3 books and we need to determine how many smallest possible numbers of the books on the shelf. So from here to here, since we have 2 books already been done, so we marked it as 18 plus 23rd position book, the smallest one, plus this book, plus this book, largest one, and from here to here we got 20 more books. So we add to it and we become 18 plus 1, 19, 19 plus 1, 20, 20 plus 20, 40, and 1 gives us 41. So our answer is option B, 41. Problem 22. What shape would be impossible to cut into 3 different looking parts of 5 shaded squares? So we have to cut the pieces in here in equal parts and see which are not the similar ones. So we are having these options. I have already counted these blocks and all blocks are 15. So we divided it into 3. 15 divided by 3 gives us 5. So each cut portion should contain 5 equal parts, and which is not possible. So let's take two option. So we consider option A. We say 1, 2, 3, 4, 5. We cut it from here. 1, 2, 3, 4, 5. This is impossible. It's different. It will always be different. From wherever you cut, it will always be different. So this is not our answer. Option B, we take 1, 2. We have some leg part in here. And we take 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's same. That's same. and that comes 5 as 1. So this could be our answer, B. We cut again 1, 2, 3, 4, 5. It will always be different because it does not have an extra leg in here. When we go in here from 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, we cut it in here, it will be always a different. It will never match. Similarly, 1, 2, 3, 4, 5, cut 1, 2, 3, 4, and 5. It will always be different. All three pieces will be different in here. 1, 2, 3, 4, 5, cut it. 1, 2, 3, 4, 5. We don't get this leg base, and it will be again this different. So our answer is option B. Problem 23. N replaces letter in the calculation can minus rho plus GA with numbers from 1 to 6 and then calculates results. The same letters are replaced by the same numbers and different letters by different numbers. What is the largest possible result she can get? These are our options. We will assign unique 1 to 6 numbers to the letters KAN, ROO, GA. We want to maximize the expression. To maximize the expression, we make sure that CAN letter, whatever we assign, should be the maximum or the largest digit number. And GA should be the largest digit number because we are subtracting, so we subtract from the lower number, so it needs to be a lowest digit number. So let's start with that. So now we take CAN. So what would be the biggest CAN we could have? We could start from 6. A we can have 5 and N we can have 4 or 3. So we put 3 in here. And the number becomes 653. Similarly, with GA, we want the largest number. So we take the largest number, 4. We already assigned A 5. So we take it as 5. So it becomes 45. Now the numbers left for us is 1 and 2. Since O is smallest, we took 122. Now we do an expression. So we have CAN minus R plus RO plus GA. So we do 653 minus 122 plus 45. And we get 576. So our answer is option C, 576. Problem 24. Janek has a strip of paper of 4 cells with numbers 1, 2, 3, 4 written in them, as shown in the diagram. He can fold the strip so that the cells form 4 layers. Among the following options, which cell's order from top to bottom is not possible to obtain? Let us go each options and see which one is eligible. Option A, 3, 1, 2, 4. The order can be achieved by folding the stripes that you can fold it 1 and behind it is 2 and then on top is 4. This can be achieved. Option B, 3, 4, 2, 1. Let's clear it first. So option B, we have, so after folding 3 would be on top, then we followed by 4, yes, and then we have 2 and then 1 at the bottom. This seems like a valid fold. Let's move on to option C. We have 3 on top, then we followed by 2 and then 1 and 4 at the bottom. Option D, we have 3 on top, 1 comes in, and then 4 cannot be because it needs to be 2. So this is not impossible and could be our answer. Option E, 3, 4, 1, 2. So we have 3 on top, 4 gets in, 1 and 2 needs to be together. So this is possible too. So our answer is option D, which is a impossible option. Great job solving these kangaroo problems with me. We have finished part C of the 2020 Math Kangaroo Challenge for grade 3 and 4 together. It was a 5 point puzzle, and you have done an amazing job solving these tricky problems. I hope you had fun and learned some cool strategies. If you enjoyed this, don't forget to like, subscribe, and hit the bell icon so you never miss a new challenge. Keep practicing, keep learning, and I'll see you in the next one. Happy mathing! Thank you.